Hi everybody, this is Professor Ross, and I'm here to talk to you about least-squares regression. This is the first video out of two discussing least-squares regression. What is least-squares regression? Well, we've been looking at relationships between variables, and we see that one of the common forms, and one of the more important ones, is when we have a linear form. And if we see that on a scatter plot, we want to be able to make some sense of that. One of the tools we've used is the correlation to help us make sense of that, and another one is going to be a line. To examine a pair of explanatory and response variables that appear to have a linear relationship, what we do is we choose a straight line. We call it a regression line that we think represents the data well. And we take a look at a couple important things. We look at how well the straight line fits or models the data. So we call this regression line a model for the data, and we want to see how well it does that. The other thing we want to do is examine what features of the line are telling us something about the data. So there's going to be some important numbers like the slope and the intercept that tell us something about the data. Let's take a look at a couple examples before we dig into the details. So here's some data we've looked at a few times: city miles per gallon versus highway miles per gallon, and we believe that this has a strong linear relationship. The correlation suggests it, and it sure looks like it on a scatter plot. And we could go ahead and take a look at the line here and try to get a line that goes through these data points and is a good model for this data. So understanding how good of a model is it, and what about the slope and the intercept of this line can tell us about these two variables. That's going to be important work for us as we look at linear models. Here's data that's less clearly linear, but it looks like we've got a big cloud of data here that might gather around some kind of linear shape, and our correlation suggests that a linear model is at least moderately okay, and we could try and draw a line through here. Now it's harder because it's less clear where the line might best go, and clearly this line is not as good a model for this data as it was for the others, but it looks like we might have reason to think it might be a decent model. Here's a data set where a line clearly isn't a good model. This is the week number and how much a movie was making at the box office. Clearly a curved set of data. If I try to draw a linear model here, there's no good way to do it. It doesn't do a good job of capturing the data in any way. So we want to make sure we make scatter plots and take a look at them and say, hey, this looks like a good set of data to use a linear model. Let's jump back to our highway versus city miles per gallon. Let's say we get ourselves an equation for a linear model that seems to do a good job, like y equals 4 plus x. We want to be able to take this equation and interpret the numbers in the equation in ways that help illuminate some things about the data. There's two numbers here, even though we don't write the slope. The slope is the number times x. It's really 1, right? It's 1x. So our slope is 1. And the intercept is the number that's not times x, so that's 4. How do we interpret these? Well, let's interpret the 4. The 4 simply says this line is crossing the y-axis at 4. What does that mean about city and highway miles per gallon? Well, it means that if we had a car that got 0 city miles per gallon way over here on the y-axis, 0 city, that our model would predict the highway miles per gallon to be 4 miles per gallon. And so we can see it's very closely related to what the y-intercept actually is. It's sitting there on where the x value is 0. And that's how we interpret the y-intercept. We say, okay, if city is 0, if the x value is 0, the model says the y, the highway miles per gallon, should be 4. Not very useful in this scenario, because who has a car that gets 0 city miles per gallon? So sometimes that happens with y-intercept. Not always the most useful measure, but it's worth looking at. The one that is always useful is the slope, so we should always look to interpret the slope. The slope in this equation is 1. That means a rise of 1 over a run of 1, right? If I'm looking at this line, it means for every 1 I go to the right, I'm going up 1, over 1, up 1, over 1, up 1. What does that tell me about city and highway miles per gallon? It says if I increase my car city miles per gallon 1, my model predicts that the highway miles per gallon are going to go up by 1. And so that's how we interpret the slope. We say, okay, if the x value, if our explanatory value goes up by 1. The slope tells us what the response value should go up. And that's useful. In this case, it's saying, hey, for the cars, it appears that city miles per gallon goes up hand in hand with highway miles per gallon goes up hand in hand with city miles per gallon at the same rate. So it's always interesting to interpret the slope, and that's something you should always do whenever you generate a linear regression equation. What else do we use linear regression equations for? These models help us make predictions. So it's a useful model because we can use it to make predictions. So for example, if we take that same one here, we can predict highway miles per gallon for cars that we don't have in our data set. Like what if we had a car that got 35 city miles per gallon? We could take our model and try and make a prediction about what the highway would be, and we can kind of do that visually if we want. But a better way is to actually use the equation itself to make the prediction. What we're saying, if city miles per gallon is 35, we're saying the x value is 35. And we can figure out what y is just by plugging in 35 for x. So 4 plus 35 equals 39. And so we would predict a car that gets 35 city miles per gallon to get 39 highway miles per gallon. And that's called prediction. You do it the same way. Whatever your regression equation is, if you want to make a prediction for an explanatory value, you just plug it in for x, and it'll spit out the y value as your prediction. Now, one thing to be careful is extrapolation. That's making predictions far outside the range of data. You don't want to do that. That's dangerous. Why? Because you don't have data that supports that. So this straight line could go on forever, but we don't have any data that makes us think it should go that way. What if we had a car that got 100 city miles per gallon? Our line predicts 104 highway miles per gallon. That doesn't make any sense. We don't have any cars that far out to know that the relationship is still like that way out there. So you want to avoid extrapolation. Stick around close to your data to make predictions. In addition to interpreting the slope and intercept, making predictions, we also want to be able to evaluate these linear models that we're creating. Linear equation is a model that we can use to try and predict outcomes. We need a linear model like that because there's variation in the response variable. There's variation in the outcomes. Let's just skip back to our highway miles per gallon versus city miles per gallon and take a look at that. What we're saying is not all cars got the same highway miles per gallon. Some got pretty low. Some got kind of medium, and some got a little higher. There was one that got fantastic highway miles per gallon. There's variation in the outcomes. What we want to say is, how good is our model doing explaining why? Explaining why some cars got low highway, some cars got middle highway, some cars got better highway miles per gallon. This model does a great job of explaining that. If you tell me the city miles per gallon, I can predict almost perfectly what your highway miles per gallon are going to be, low, medium, high. I can explain it really well. So that's what this measure is going to help us understand. The way to judge how well our model is doing this by taking the correlation R and squaring it. The square of the correlation can be interpreted this way. It's the fraction or the percent of the variation in the values of y, our outcome. That's explained by our least squares regression of y on x. So what we're looking for is a high percent. We want models that do a good job of explaining the outcomes. Anything over 50% is actually really good. It means you're explaining over half of what's going on in your outcomes. So you want to have a sense of just that lower values mean it's a worse model, higher values mean a stronger model, but we also want to interpret it explicitly. So, for example, our carbon emissions and South Pole temperature, the R value was, let's jump back there quick, R value was 0.545. If I multiply that by itself, 0.545 times 0.545, I get this number, 0.297. I can think about that as a percent, 29.7%, and that's somewhat low, right? It's under 50%, so the model's not as strong. Clearly not as strong as a couple of the other ones we've looked at. But what is it saying more specifically? It's telling us the percent of variation in the values of y, in the values of the South Pole temperatures, the percent of variation in the South Pole temperatures that's explained by our linear model based on carbon emissions. So if I have carbon emissions and I have this model that I've created, I can explain about a third of the changes I'm seeing in South Pole temperatures. And that's actually a pretty good chunk. I mean, there's a lot of stuff going into why temperatures are what they are. If I can explain 30% of what that is, that's not too bad. Let's compare r and r squared and see how these two compare, because it's a little bit different interpreting the two. Here's Pearson's correlation r. We've seen this little chart before. 0 means no relationship. As we move out towards 1, we get to strong relationships. Well, if I square each of these, 0 squared is 0, 0.25 squared is 0.0625, 6.25%. 0.5 squared is 25%, 0.75 squared, right, all the way up. These interpretations don't change. A 0.5 correlation is a moderate relationship, and it goes along with a 25% on the r squared. That's telling us our model's doing a moderate job of predicting. So we were just over that. We were a little bit above 0.5. We were a little bit above 25% at 30%. So we were a little bit better than a moderate relationship, a little bit better than a moderate model. So you can kind of get a sense of what's going on. If you're at a 0.75 correlation, that's quite strong. Your r squared is going to look like this, 56%. You're explaining over half of what's going on in the outcome. That's pretty impressive. Of course, all the way up at the top, 100%, we would rarely ever see, but it would indicate a perfect model. All right, so judging your model through r squared is an important part of what we're going to do with our linear models. One other aspect that's going to be important for us to understand how these models, even where they come from, is looking at differences between our predictions and our actual data. How well does a given linear model predict outcomes on the response variable? That's what we've been talking about. One way to examine it piece by piece is called the error or the residual. Error is the difference between the y that the line predicts and the y in the data. So on a graph, what we're talking about is the vertical line segment, the length of that from the data point to the line. Let's look at an example. Let's go back to our South Pole emissions data. Here's a linear regression model. Y equals intercept plus slope times x. And so we can use that to make predictions. Let's say we were going to predict it for 340. We take 340 and plug it in here for x, multiply it by this, add negative 20.2, and we get a y value of predicted temperature. There it is. This blue dot is our model's prediction for 340, and it looks like it's just above negative 4 degrees. Now, how does that compare to the actual piece of data in the data set? What's the actual temperature? There's the actual temperature, circle that here. The actual temperature was lower than our prediction. So we have an error. We have it's off from what the actual data was. How far off is it? This little distance here, that's called the error or the residual. We can see it's about 1.5 degrees, right? If I actually calculate it, what I want to do is I want to take my piece of data, my y value, subtract the prediction, and it'll tell me how far off I am. Negative 4.9 was the actual, minus negative 3.778, that's the prediction, and I get the error, negative 1.122. Whenever your actual data is below the prediction, you get a negative error. Whenever it's above, you get a positive. Can you try one for yourself? Let's say we want to find the error residual when carbon emissions was 330. Try it out. See if you can find the prediction. Here's the actual, and we'll take a look at the error in a moment. Here's the predicted. If we plug in 330, we get negative 4.261. So if we subtract negative 2.1, the actual, minus our predicted, negative 4.261, we get a positive error, 2.161. Why are errors important? Well, what we're going to look at is all the errors collectively. And what we want to do is we want to make all the errors collectively as small as possible, and that gives us the best possible model. That's what we'll get into in the next part of this video.